Well, thank you very much for following us here at MobiliT.AI. We've had a small technical difficulty, so it's a take two for us. And we're glad to have with us Liam Paul, who is an assistant professor at the University of Montreal. He's a director of the Laboratory of Robotics and Embodied and Artificial Intelligence of Montreal, or the REAL. And his lab focuses on robotic issues, including building representations of the world, such as with simultaneous localization and mapping, modeling your uncertainty, and building better workflows to teach robotic agents new tasks. His presentation will be titled Quantifying Uncertainty in Deep Learning-Based Perception Systems. Here is Liam Paul.
Okay, merci Raymond. Thanks, Raymond. I'll try and catch up a little bit of time since we lost a little bit of time from the technical issues. Let's see if this works. So, oui, bonjour à tous. Si vous avez des questions en français, tu peux me demander les questions en français. Je vais faire la présentation en anglais, but I can answer questions in both languages. So, yeah, as Raymond mentioned, the topic of the talk is on quantifying uncertainty in deep learning-based perception systems. And I really view this as a prerequisite for deploying embodied systems that have these kind of deep learning based models. We have to be able to reason about not just the outputs, but also have some measure of uncertainty associated with the output. So I'll start by giving an example that I like to show of a situation where robots work really well. So please let me know if the video is not working. So in this situation, this is the Amazon warehouse, and these robots move around and they pick up the shelves and they bring the shelves to packers who pack your boxes. And the system is so efficient that your box is packed within 12 minutes of you placing your order on Amazon. And I think what's interesting about this system is that it's been orchestrated and engineered in a way that the environment and the task is extremely deterministic, right? All the shelves are exactly the same. The floor is extremely smooth. The widths of the corridors are exactly the same. And there's no people who are moving about. There's no obstacles whatsoever. So in these particular situations, robotic agents are able to work extremely well because the world is very predictable. We're very easy to predict. There's very little uncertainty, in other words. On the other hand, in situations like autonomous driving, or in particular, autonomous driving in certain parts of the world where the driving task is a little more chaotic, there's just absolutely no way we could deploy a robot into an environment like this. Yet humans are able to operate in these conditions, and actually the utilization of this intersection is relatively efficient. I mean, the throughput through this shared resource is actually extremely high, regardless of how chaotic it seems. And in the middle, what's going on is all of this negotiation between people, but also implicit reasoning about the uncertainty with respect to what other agents are likely to do and how your actions will impact them, and et cetera, et cetera, et cetera. So if we want to make steps towards getting, from the controlled environment of the Amazon warehouse to robots in the real world, in chaotic situations like this, one of the major tools that we need is to be able to quantify and reason about uncertainty, both in at the present time, but also uncertainty of things that are likely to happen in the future. So I'll give just a very brief background of what the traditional robot system looks like. And I put traditional here in brackets because makes me feel old, but this is the way I view the abstractions of a robot system, as opposed to just a deep neural network on a robot. So there's really, on the world or plant side, this is the part that we cannot control. This is the design of the robot, and we're assuming that we're only operating at the level of software here. We can't control the design of the robot explicitly. And so the robot has actuators, it interacts with the environment, and it gets information about the environment through its sensors. So everything above this blue line in the agent category are things that we have control over. And typically, robotic agents are constructed with these 4 key building blocks or abstractions. The first is the perception block, which takes this stream of unstructured sensor data and turns it into something that's actually understandable in some way, that turns it into some useful measurement about some state of the world that we believe to be of interest. This estimation block takes this stream of measurements and synthesizes them all together into one coherent representation of the world. This we usually refer to as a belief. This belief is used to make a plan, which is like under nominal conditions, how we might execute the task that we're trying to execute, like driving. And then this plan together with the belief are sent to some controller, which is tasked with actually executing that plan. And so, you know, in all of these components, what I'll argue today is that like the perception system is really the producer of uncertainty. And then the estimator and planner and control blocks are really the consumers of uncertainty that need to be able to reason about uncertainty to achieve their tasks in many cases. So specifically today, we're going to talk about deep learning and perception. And our objective is to really provide calibrated uncertainty estimates from the perception system to be used downstream. And I'll be more precise about what I mean by calibrated uncertainty estimates in a minute. Okay, so the outline: why do we care about uncertainty? How do we measure uncertainty? What does it mean for uncertainty to be calibrated? And then I'll talk about a recent method that we built in my lab, which I'm really excited about, which is called FCal, which produces explicitly calibrated measures of uncertainty. Okay, so first, why do we care? What are the real applications here? Well, I'll lump them into two tasks. One is for, one reason why we might care about uncertainty is for uncertainty-aware downstream tasks like planning and control. And the other reason that we might care about it is for that estimation or sensor fusion block. So downstream, we might care about uncertainty for a number of reasons, but one might be safety critical applications. So for many of you maybe have seen this video before. This is the video of the Uber pedestrian fatality in Tempe, Arizona in 2018. And there have been a lot of reports that have come out about this, but one of the key findings was that the reason that this cyclist was not detected was because there was some uncertainty about whether it should be determined as a pedestrian or a cyclist, and there was some kind of thrashing in the perception system. And in the end, neither choice was taken, and the results were catastrophic. So in this case, if we had instead a perception system that was able to output some kind of probability over the possible classes of this object, like I'm 50% sure it's a pedestrian and 50% sure it's a cyclist, then there would have been some probability, some possibility that the downstream controller would have said, well, in either case, we need to stop, so we should just stop. The other case, which is less safety critical, but is more related to efficiency, has to do with taking actions. So in a lot of cases, we want to build controllers that are actually actively able to reduce their uncertainty. For example, if there's some element of the world that we're not sure about, then we want to take actions to actually reduce that uncertainty explicitly. And so this is some work that we did in my lab a couple of years ago, where this robot is tasked with figuring out where it is inside a room. And to do that, it needs to take actions that explicitly help it disambiguate its location by looking at its sensor data. And the novelty of this particular work was that this was done completely in an end-to-end differentiable fashion, where we could like learn these sensor models, but still account for uncertainty explicitly. So the other case where we really need uncertainty measures, and specifically calibrated uncertainty measures, is inside this sensor fusion block. So this is a re-representation of the figure we saw before. So the output from this perception system is some kind of measurements about the world that we care about. And like, without getting too much into the details, these sensor fusion algorithms are all based on some Bayesian fusion approach, where we need to estimate the probability of our state given all the measurements. And the way that we do this is through some approximation of like a Bayes filter, which decomposes this as the measurement likelihood times a prior divided by the evidence. So the key part of this equation here is that we need this measurement likelihood. So what does this mean? It means that the perception system has to not only output a measurement, but also a likelihood associated with that measurement. And what that likelihood, explicitly means is some measure of uncertainty about the measurement, so that this estimation block can know how much it should trust that particular measurement and then fuse all those measurements together in some optimal way. Okay, so hopefully you're convinced that we should care about uncertainty. Maybe you're not, but I don't know, did my best. So part two, how do we measure uncertainty? So let's start with the old school way. So if I was an old school roboticist, which I might or might not be, then if someone handed me a new sensor and told me how it worked, this is what I would do. I would take that sensor, I would use my intuition about how it works to write down some model. So let's say, for example, this sensor is a single beam rangefinder, like it shoots out a beam and then it measures how far away the object is that that beam hits. Well, so I can write down a model based on geometry that says that, okay, the measurement that I get, minus the location of the sensor should be the Euclidean distance, which is represented here by the L2. And then maybe there's some noise on the sensor because there's some stochasticity to the sensor and it's not going to give me the exact same reading every time. So the thing that I really need to characterize, so that noise is represented by this mu term here, or nu, or whatever that is. So the thing that I really need to characterize is what this noise is like. So what I would do is I would construct an experiment where I would strap my sensor down, and here's like a coarse kind of picture of something that looks like that. Strap my sensor down, put an object in front of it, measure the true distance between the object and the sensor very, very precisely, and then take a whole bunch of measurements and characterize the noise based on my knowledge of the ground truth, and then find a distribution. And that's how I would find the parameters for this noise. The problem, the problem in the case of deep learning for perception, we want to treat the deep learning system as if it's a sensor, but this process is completely impractical. There's many, many reasons why. First of all, we can't construct, controlled experiments for every single possible image input that we might get from our camera. There's also this assumption that the noise is homoscedastic, which means that the variance of the noise is independent of the actual measurement. So, in that case, if that's not the case, then I need to redo this experiment for every single possible sensor data that I might get. And this is the case with deep neural networks. So we need another way of trying to evaluate uncertainty estimates. So the other issue with deep learning in particular is that there's more types of uncertainty than just the noise that's associated with my sensor data that I had in the case of my sensor. And this is due to the fact that my model was trained, and there might be some uncertainty that's due to the fact that I haven't seen any inputs like the one that you're showing me at test time, and so I'll be uncertain about the output. And so a typical decomposition, there's more types of uncertainty than this, but a typical decomposition that's used these days is the distinction between so-called aleatoric uncertainty, which is exactly the noise, the uncertainty that we were talking about in our sensor calibration case. That's the type of noise that is completely irreducible and part of the actual stochastic process of the system that we're trying to model. And then there's this other type of uncertainty, epistemic uncertainty, which is reducible. In the case where we would have infinite data, then this epistemic uncertainty could go to 0. But in practice, we have an imperfect model. We might have picked the wrong model class. We might not have enough data. We might also be out of distribution in terms of the test data that we're getting. We might not be well represented by our training set. And so what this picture on the top right, which is stolen from the seminal paper from Kendall and Gall, is trying to show if you sort of stare really closely at it. So what we're doing here in this example is doing an image segmentation task. We're trying to classify every single pixel in this image. And in the aleatoric case, you'll see that there's high uncertainty over pixels that you or I would have a very difficult time classifying properly anyways. They tend to be at the border between classes. So like, is this, the border between the sidewalk and the road is inherently uncertain. Some people might have classified those pixels as sidewalk, and some people might have classified them as road. In the epistemic case, it's clear that this should be sidewalk, but for whatever reason, our model has not seen good data representing sidewalk, and so we have high epistemic uncertainty on the sidewalk. But if we got more data of sidewalks, that uncertainty would go away. There's also a distinction between the case when we're doing a regression problem and when we're doing a classification problem. So this is actually an example of the work that I did when I was a postdoc at MIT, where we built this autonomous car that was going to do end-to-end driving with imitation learning. And right away, we hit this problem of, in the case of regression, we're just trying to regress one value, whereas in the case of classification, we're trying to output a distribution over classes. And a lot of the different uncertainty estimation techniques only apply to one or the other. In fact, in general, I would say it's probably easier to identify at least epistemic uncertainty in the classification case. So what we did here is, instead of mapping our sensor input directly to a steering value and regressing it, we discretized the output into a set of bins and then did a variational Bayesian approach to actually find the distribution over the bins so that we could actually quantify the uncertainty over the output. Okay, so let's talk about different ways that we can actually estimate these two different types of uncertainty in deep learning models, either the epistemic or the aleatoric. And in each case, I'll make a little note on the slide of whether it only applies to the classification case or it applies to regression or both. So the first thing that you could do is you could do this softmax thing. So this gives you a distribution in the case of classification. But I won't go into the details, but we really should not treat this output as having any theoretical grounding in terms of calibration of uncertainty estimates. If this is used for our uncertainty estimation, then we are destined to be overconfident. Another idea is that we'll initially randomly initialize a whole bunch of models, say n, and then when we get a new piece of test data, we'll run it through all of our n models. And if there's a high discrepancy between the output that we get, then we can say that it's probably uncertain, since it's due to more of the random initialization of the networks than it is to the actual prediction. A similar idea is the idea of Monte Carlo dropout. So in dropout, we only have one model, but we randomly turn off neurons in the hope to avoid overfitting. In Monte Carlo dropout, we also do this at test time. So one idea might be that if we do multiple passes of our neural network with different neurons turned on and off, and we get a high discrepancy at the output, similarly to the ensemble idea, we might infer that we have high uncertainty about this prediction. There is some theoretical grounding for this as a Bayesian approximation, but in practice, it doesn't work that well, and the training is really slow. Another idea that only works for classification that I actually really like is the idea that somehow inside the representation of the neural network, we can embed these representations on some manifold, and that each class will somehow nicely cluster on some manifold. And then when we get a new piece of test data, we can look at how far away it is from all these clusters. And if it's far away from all the clusters, then we could say that, well, we haven't seen a representation that looks like this, and so we should probably be pretty uncertain about the output. And then finally, the right way to do this is actually to actually maintain a distribution over all the weights in your network. But this is very hard to do, in practice. In the case of aleatoric uncertainty estimation, now we're not so concerned with out of distribution uncertainty, but more the actual calibrating with respect to the actual process uncertainty. And so, one idea could be that like in the regression case, we'll just try and regress the parameters. So instead of parameterizing the output as a mean, as just a mean, and then a variance associated with it, say if we parameterize things as Gaussian. The problem is that we never get labels for the variance. We just get labels for the actual true thing. So an idea that's proposed several years ago is this idea of loss attenuation. So the idea here is that we're going to take our typical regression L2 loss, which is in the middle here, and we're going to scale it by some variance parameter. So this means that if the network somehow figures out that it's unsure about an output, it can jack up this uncertainty measure, and that will make the loss go down. The problem is that there's a degenerate case here where it can just jack up the uncertainty estimates for everything. And so we need to add this like regularization term at the end to sort of penalize jacking up the uncertainty estimates. So the problem here is that this assumes a Gaussian noise model, which might or might not be true. And also there's no guarantees on calibration here. And so these are the things that we're going to address next. Okay, so what does it mean for uncertainty to be calibrated? I'm going to go this, I think I'm kind of running over time, so I'll go through this fairly briefly. So the idea here is, what it really means for an estimate to be calibrated. I think the easiest way to think of it is in terms of quantiles. So say you took a test, a standardized test, and you were in the 80th quantile, the 80th quantile. That has a specific meaning. That means that if we picked random people out of the population, that 1 in 5 should be better than you, and 4 in 5 should be worse. And if that's not the case, then your assessment of being on the 80th quantile is not correctly calibrated. So projecting that to the object detection case here, what we want is that if we were somehow able to repeat this experiment again and again and again, that the distribution over outputs that we would get would match the true distribution over the labels that different people would make if they had to label it over and over and over again. But the problem is that typically we don't have many labels over and over again. We only have one. So it's kind of an unobservable thing. And so the way that we're going to evaluate this is actually looking at this kind of idea of quantiles. So if we have this predicted quantile on one axis here, and we have the actual quantile on another axis, then in the ideal case, our curve here should exactly follow the red dotted line, should exactly go on a diagonal. But if we can look at our system and actually evaluate it somehow, then the error that's the absolute value error between the diagonal and our thing is going to be the metric that we're going to use to evaluate how good our calibration is. And this thing is called a reliability diagram. Okay, so without going into too much of the details, I'm going to try and give you an overview of the method that we proposed for aleatoric calibration, uncertainty calibration in the case of regression. And we specifically applied it to the problem of object detection. So quick overview of object detection. Object detection is interesting and hard because it's actually a joint inference problem over, it's a joint classification and a regression problem. We have to, on the one hand, specify where something is in an image and also specify what it is in terms of a class. And so the way that this works in general is that for the classification part, we can have a standard softmax and a cross entropy loss. And then for the where is it part, we can have some ground truth bounding box position from what someone drew, and then we can do an L2 loss. And we can mix these together somehow to train our object detector. And this is old school stuff, but the way that this is typically done, or a way that's very famous, is the so-called region CNN family of approaches, where the faster CNN has some kind of CNN backbone, which generates feature representation. And then it tries to find region proposals through this RPN, this region proposal network. And then these region proposals are classified individually. So we can get a whole bunch of classes and bounding blocks for a whole bunch of images. So the idea of FCal is that we're going to take this original loss attenuation formulation that we saw before. So remember what this is doing is it's taking the L2 loss and allowing some give for the output to assign high uncertainty to cases where the error is high, but also penalizing adding uncertainty. And so this loss is applied over every sample. But I think the intuition that we made here is that really to apply calibration, we can't enforce calibration over a single sample. It doesn't make sense to say that one single sample is calibrated. We really need a group of samples and then to enforce calibration over this group. Well, in deep learning, we have batches, like we treat our data in batches. And so like the intuition here is that what we're going to do is we're going to evaluate this loss attenuation formulation. But then once we've collected all of these losses for a batch, we're going to enforce that the actual distribution over the batch actually matches some calibrated distribution that we can generate. And the trick for calculating this calibrated distribution is that if each output is supposed to be a Gaussian, then we can square them and add them, and that gives us the chi-squared distribution, which for very high k is also approximated as a normal distribution. So basically, we can calculate the distance between the distribution that we got from all of our outputs and how, like, the distance between that and the true Gaussian distribution that would have been created by truly Gaussian variables that were added and used to create this chi-squared distribution. So now we have this like variational loss, this distance in distribution space that we can minimize at the level of the batch, and we add this or complement the loss attenuation formulation in this way so that we can guarantee calibration. Okay, so I think maybe I'm really running over time. So the idea here is now we're going to have, our input goes through a neural regressor. We predict the mean and the uncertainty. For each mean, we find the deterministic regression loss, but then we plot these all and we enforce consistency, distributional consistency over this. And this loss is just the sum of some supervised loss, the L2 loss, plus lambda times this FCal loss. Okay, so like quick results. Our results show that compared to just loss attenuation, we're actually significantly more calibrated in our output, which is shown on the right-hand side here with our reliability diagram, and on the left-hand just empirically by looking at how much closer our distribution is to the target distribution. And then another interesting finding is that as we vary this lambda parameter, we can see that there's some kind of trade-off between the deterministic performance of our object detector and the calibration. And so this got us to thinking, like, if there's a trade-off, it must mean that the two elements of our loss are actually competing. And so we did some further experiments, and what we found, so what this plot is showing is for a true noise distribution that's a gamma distribution, the shape parameter, as the shape parameter goes up, it approximates closer and closer to a Gaussian distribution. And so what this plot is showing is that as our model assumptions become correct, the performance trade-off becomes less. So what's really cool here is now we actually have some way, by looking at the performance trade-off, the performance calibration trade-off, of actually evaluating how good our distributional model assumptions are in the first place. Okay, so the key takeaways from today, I think calibrated uncertainty estimation is a requirement for integration of deep learning models into embodied systems. There are different types of uncertainties present in learning-based systems, and we need to reason about them differently and explicitly. And finally, we presented a way of explicitly enforcing calibration for aleatoric uncertainty estimation, specifically for regression, and applied it to object detection. So thanks, that's all I had for today. Sorry if I went over.
Liam-Paul, thank you very much for this presentation. I don't know for the other participants, but I'm left with wanting more. We don't have much time for the questions, so what I suggest for the participants to MobiliT.AI, if they want to get a hold of you, they can do so through the Swapcard platform, just linking with you. and they can continue this conversation with you, Mr. Paul, afterward. So I invite the participant to do so. And thank you again for this presentation today.
My pleasure. Thank you.